Hello students, greetings to you. We will continue our discussion on the batteries as well as a little bit about fuel cells today. Yesterday I had talked to you about nickel cadmium cell that is essentially similar to nickel iron cell, and I had shown you this slide, and now I want to compare some of the alkaline rechargeable battery systems and the typical applications. Actually, whenever we want to tell something about the batteries etc., if we do not talk about the applications and salient features, it will be some sort of a anticlimax, because quite often we have to choose between various kinds of batteries. So, look at nickel cadmium battery. It is a prismatic cells with pocket electrodes etc., and battery applications include remote power, load leveling, stationary, and then the salient feature. Among the salient features, you will see that the toxicity is one part in which I want you to concentrate, and the other one is the limitations. So, in nickel cadmium batteries, you can see that the energy relatively low efficiency per volume and weight, that is not very highly desirable. So, open circuit voltage cell capacity should be about 1.3 volts, but toxicity due to cadmium is always there. That means, once the useful life is over, we are faced with the burden of cadmium. Ditto with other types of cells. Here in prismatic cells, pocket electrodes, sintered electrodes and powder, these are all different kinds of electrodes of different sizes etc. For example, this prismatic cells having sintered electrodes are used mainly in aircraft batteries, and again toxicity of cadmium should be common. Then button cells are there, nickel cadmium, low power applications, but toxicity, we really do not know how to recover very low quantities of cadmium, even though we know that they are dangerous in the environment. Similarly, sealed cylindrical cells are there with jelly roll electrodes. These are useful for very high power, but portable energy. So, relatively low electrode efficiency is one of the common result that happens whenever we draw high power current. So, look at nickel hydrogen battery, again a similar problem. Pressure vessels, thin electrode stacks are required, and high profile applications in space missions. Now, usually they do not use anything else apart from nickel hydrogen in space applications. So, as power systems for military, satellite applications etc., only nickel hydrogen are useful. Again, the energy, other things are essentially same, 1.3 volts, 60 watt hours energy density etc. Then there is this nickel metal hydride is something special, only that has come to the fore only since last 20 years, and these metal hydrides are portable, high power, high energy applications. So, apart from that, there is not much to tell. I want you to study all these applications with respect to their utility. Then comes silver zinc prismatic cells with the flat plate electrodes used in military applications and marine communications. They are expensive because of the use of silver. You see, silver is an electrode that is not only toxic, but it is costly also. So, but current capacity wise and all, it is very good, 1.6 volts and 190 volts watt hours, and then specific energy is approximately 90 watt hours per kg etc. And MnO2 zinc electrode, sealed cylindrical cells, applications portable, low moderate power applications. Suppose you want to monitor SPM, SO2 etc. in the environment where in the field, then you should go for such electrodes, batteries. They are relatively cheap and absence of lead and cadmium etc., makes it environment friendly. They are alternates for primary alkaline batteries. Energy density is also quite attractive. I will not go into details of this, but these slides we have prepared for you to study and compare. Okay. Rechargeable battery systems under development, I want to give you a couple of remarks. Lithium manganese oxide is 3 volts. Look at the research emphasis in getting higher voltage for the same electrodes, and then remarks, of course, I have put starting from the applications. So, room temperature operation means very comfortable. Positive electrode material is air sensitive. So, problems due to plating of lithium, because the high, if you want high voltage, lithium should be very minimum. So, plating of lithium is required. Then lithium, this is another trademark battery available in the market commercially, 2.5 volts. Lithium titanium S2 is 2.3 volts. We are having nothing better than that. Comparable would be sodium nickel chloride. This would be approximately 2.5 to 2.3 volts, but very good. But they need high temperature molten salt as catholyte and solid Al2O3 separator, beta alumina, that is Al2O3. Here the problem is they would be useful only for specific applications rather than as a routine battery thing. Similarly, sodium sulfur 2.1 volts beta alumina separator, high temperature liquid electrodes, difficult to handle, but useful anyway. So, the chemistry involved in all the above 3 types of nickel cadmium batteries is essentially same. We have already written the equations. Basically, it is conversion of cadmium to cadmium hydroxide with the release of 2 electrons, and the normal reaction would be beta nickel hydroxy peroxide acid, water plus electron, that goes to beta nickel hydroxide and OH minus. So, however, this reaction is basically complicated. You can imagine, you see this is a peroxy compound and here it is only hydroxide. All the reaction that is happening is only due to this electron. That is fantastic. So, this reaction is definitely complicated because of the existence of 2 additional phases that undergo electrochemical transformation under various conditions, and this is the type of solid state reaction we write, that is Y moles of NiOOH and 1 minus X of H2O plus E minus goes to alpha nickel hydroxide with X, and that is X means variable water, variable quantity of water plus OH minus. So, the gamma nickel peroxide hydroxide phase appears in the system because of the possible overcharging of the beta NiOOH electrode. Now, let us talk a little bit about nickel hydrogen batteries. That makes it very simple, H2 plus 2 OH minus goes to H2O, and pressure vessels made of Inconel or stainless steel, they can withstand up to 200 bars. What does it mean? This 200 bars essentially are used, such conditions prevail in submarines. So, that is why we need an alloy like Inconel. And other batteries are there, manganese dioxide, zinc battery, silver, zinc, alkaline battery. There are various batteries are available, and they would be having specific applications. We will not go into details of this, except to say that there are lot of reserve batteries. There has been a requirement of cells with special characteristics for the use in proximity fuses, artillery, mines, balloons, guided missiles, radars, bazookas, night viewing equipment, and several times walkie-talkies and several types of materials require these kind of batteries, and they must have capability of high voltage as well as long inactive shelf life. This is very important. We want the batteries to have long shelf life even if they are not used. So, the moment we use it should come into life. So, rapid activation is one of the requirement for a good battery. So, here I can say a little bit about perchloric acid and fluoboric acid cells, that is essentially lead, perchloric acid, fluoboric acid and lead oxide. Reactions are similar. Lead goes to lead ion releasing 2 electrons, and perchloric acid reaction produces lead perchlorate, and this is another reaction PbO2 plus Pb. So, similarly we can talk about that is the silver chloride cell, that is also very good, and Gordon magnesium battery. This is one of the important batteries containing magnesium as the negative electrode and oxygen depolarizer as the positive electrode. Here the most beautiful thing is tap water is used as the electrolyte. So, we can simply write a cell reaction like magnesium as one electrode, water as the electrolyte, or KBr we can add. KBr means potassium bromide in aqueous solution. So, water also is one of the electrolyte plus oxygen gas from the air, then carbon as the another electrode. So, silver peroxide zinc alkaline cell was designed during the Second World War to meet the requirement of high rate primary cell. However, during investigations we find that the cell was best suited for one shot purpose because of the shorter shelf life arising out of the high solubility of silver oxide in NaOH or KOH. That is why these cells are almost obsolete now. Nobody uses this kind of cells in silver oxide KOH because they are all one time cells. So, you are ready to forego the reuse, then you can use this type of cells. Then the reactions at the silver oxide electrode occurs in 2 reduction steps. First is silver oxide goes to Ag2O, this is AgO, and then Ag2O goes to Ag, that is silver. So, at the zinc electrode again we have the final product would be K2ZnO2 plus 2H2O. So, the overall reaction at the zinc electrode you can write, that is zinc plus 2K plus 4OH minus goes to K2ZnO2 plus 2H2O plus 2E minus. So, that completes our discussion on various kinds of cells, that is battery cells. We have discussed about nickel, cadmium, air water, silver oxide, and then the lithium batteries, and then nickel, air, all those things. Now, I will introduce you quickly to another part of the electrochemical technology, that is known as fuel cell. We will not go into details, but we will just have a glimpse of what is a fuel cell. This is for the sake of brevity, that we should not leave out anything related to electrochemical technology that is used in the pollution monitoring. So, what is a fuel cell? A fuel cell is an electrochemical cell that can convert chemical energy contained in a readily available fuel oxidant system into electrical energy. So, they work at high efficiency, resulting in emission levels that are for the far more than the permissible limits. So, they are modular in nature, they can be built in a wide range of power requirements from a few hundred watts up to multi kilowatt and even megawatt sizes. See, here the beauty of fuel cell comes into play. You know, the fuel cells are required not only on the earth, but even in space applications where a rocket or a satellite has to keep on working for years together based on its own chemical system. Basically, what is a fuel cell? It converts electrochemical chemical energy into a reusable electrical system. So, the chemical must be released slowly, so that electrical energy keeps on being supplied to the system. So, it works for longer time. So, what are the basic theoretical principles? Very simple. We have a chemical energy that goes to heat, then it is mechanical energy converted and then into electrical energy. So, we need a fuel, we need an electrode and we need another electrode and we need an oxidant. So, both oxidant and fuel can combine to give you electrical energy. So, there are several types of fuel cells, with hydrogen oxygen fuel cell having porous electrodes and potassium hydroxide as the electrolyte. Simple reactions, O2 plus 2H2O plus 4E goes to 4OH minus, and the cathode reaction above is the sum of the intermediate reactions occurring at the cathode, that is 2H2 plus 4OH minus plus 4H2O plus goes to 4 water and 2 electrons. These 2 electrons are again used up here, and the overall reaction would be 2H2 plus O2 goes to 2H2. So, the products of the fuel cells are always water and maybe a little bit of carbon dioxide, depends. So, the fuel cell electrode design normally provides for high rate of electrode processes by creating stable interface between the 3 phases, that is solid, liquid and gases. So, all these 3 must be used up and thrown out, used up and thrown out, used up and thrown out. Some of the electrodes used are platinum, porous PVC and Teflon coated with silver, nickel boride, rainy nickel and many of the simple metallic systems which we are quite familiar in our day to day industrial life. So, what are the oxidants? The oxidants include oxygen, air, hydrogen peroxide, nitric acid, any of the oxidant will do the job, and oxygen is used as the oxidant in many fuel cells because it can be attached in a cylinder, and then the cylinder can be opened at with a needle valve to supply very small quantity of silver, oxygen continuously to the system, so that the fuel cell keeps on working. So, the reactions proceed at a faster rate at increased temperature and also in pressure, increased pressure also with suitable catalyst. So, here is a fuel cell system stack, here is the fuel cell stack. All other things are normally systems required. This is a system nothing to do with the fuel cell. This is some other system. I am not going into details of what is this. It is a catalytic converter reactor, okay, in a petrochemical complex, but the power supply is from fuel cell stack here. So, this kind of applications one can use especially in refineries and satellites and other places. So, from the practical point of view, fuel systems are like this. Alkaline fuel cells are there, and then molten carbonate fuel cells, phosphoric acid fuel cells, solid oxide and proton exchange membrane fuel cells. So, alkaline fuel cells equipped with a dual loop water removal system. Here you can see that the electrolyte is KOH again, and then the pressure hydrogen comes here, hydrogen fuel cell. So, there is a reaction with the KOH producing water. Here also it is a similar kind of reaction. This is a sort of mirror image, left and right, but both of them are working in tandem. So, this is a alkaline fuel cell called as dual loop water system also. And then molten carbonate cells, we can simply write the reaction with very simple components, that is hydrogen and carbonate goes to H2O plus CO2. That is very simple known reaction like soda. Okay. So, what will be the outcome of soda, that is what you drink at home, bicarbonate. So, carbon dioxide and water. So, products are always harmless, especially in fuel cells, that too in molten carbonate fuel cells. So, cathode reaction we write 1 by 2 O2 plus CO2 goes to CO32 minus and COH2O goes to H2 plus CO2. So, coal fueled MCFC power plants have been developed by international fuel cells for electrical utility and dispersed power generation. Then there are reactions occurring in a phosphoric acid plant with a fuel cell with matrix electrolyte. Here I have phosphoric acid matrix, H2CO2 comes here, and this is a sort of a electrode, plate electrode. This is another cathode, and reactions are very simple like what we have studied so far. Anywhere all the time, only simple reactions like H2 goes to 2H plus and oxygen goes to water. So, phosphoric acid fuel cells are considered to be most advanced fuel cells. After the alkaline fuel cells, they are used in spacecraft. So, they have been operated with a wide range of power output 1 kilowatt to 5 megawatts. So, we are not talking of small power requirement, but also in megawatts. So, the reaction occurring here with a matrix electrolyte are represented, I have already shown you the figure, and the electrolyte is contained in a silicon carbide matrix. You can't have the electrolyte liquid hanging around in space applications. They have to be incorporated into a solid substance, so that liquid is available all the time. At the same time, it should not spill out and cause corrosion and other related problems. So, the silicon carbide matrix is normally placed in between the electrodes. The bipolar plates are normally hot pressed carbon or graphite plastic mixture. So, such fuels are developed for US Army. They have reached India, but we do not produce them in India. And we have also tried using them in electric vehicles and then power plants, etc., but it is slightly difficult right now to adopt them on larger scale, because the technology has not been available, and as far as fuel cell technology is concerned, India is something like underdeveloped country. So, let us discuss a little bit about ion exchange membrane fuel cells. These are also very simple systems, essentially same reactions what we have discussed earlier. This is developed by GEC, General Electric Company, and a solid polymer electrode has been used. You see, these solid polymer electrodes, these are all patented products which are not available in the free domain. That is why all these applications make the space travel, space applications very costly. We have to import them and pay in dollars. While in orbit during shady periods, the actually fuel cell provides energy for the space station. That means power required would be huge, and during sunny periods, of course, one can go for solar cells. Then there are solid oxide fuel cells, very simple reaction as usual, x moles of H2 plus CO plus x plus Y O2 minus goes to water CO2 and E minus. Simple reaction cathodic, oxygen plus electron goes to O2 2 minus, that will combine with water to give you water and CO2. I have put x and y to indicate that the quantities can be varying than the stoichiometric requirement. So, a fuel cell requirement is again one electrode here, one electrode here, this is cathode, this is anode, and the transfer of the electrons takes place in between the electrodes. We have unused oxygen we supply oxygen on one side and hydrogen on the other side. So, biochemical fuel cells are also there, which will normally having specialized applications. For example, urea and glucose, very simple reactions, but they act as a fuel which is oxidized with the help of living organisms, biochemical cells. So, what are the living organisms that can oxidize substances? Everyone, including us. We oxidize glucose to survive. Bacteria also do the same thing. Enzymes derived from bacteria are basically the catchers of glucose, and then they release the oxidation products. So, it is possible to accomplish direct reduction of oxygen or some other oxidant at the cathode, that is biocathode. So, they can be used to generate reactants that are consumed at the electrodes itself. Then there are regenerative fuel cells. Here the photogalvanic cell is something like a chemical. Nitrosyl chloride is photochemically dissociated into nitric oxide and chlorine, which are used as fuel in fuel cells. The fuels are regenerated photochemically. That is very interesting. And now last one, solar cells. Direct or diffuse solar energy can be converted with the help of solar cells directly into electric current and photovoltaic current without intermediate conversion of thermal energy. This principle everybody knows, is not it? Nowadays we have all over the world solar energy available and solar panels etc. very highly developed, but the problem is with higher energy conversion is still a dream as far as solar energy is concerned. Normally we expect solar energy to be very efficient, unfortunately it is not. Maximum solar energy conversion what we have obtained so far in our research laboratory is approximately about 19%, not more than that. But 90% of the solar energy conversion units give you only about 13 to 14%. If they cross 14, it is considered to be simply super panel. So, with this we come to the discussion on the electrochemical cells, and in the next class, that is our last class, we will talk about process waste handling and zero liquid discharge systems. So, thank you very much. We will meet again.